As our fifth team, I'm delighted to introduce to you the students team from the Hebrew University of Jerusalem.
Thank you. Good morning, everyone. Would you like to save over $500 million in cost and close to 40% in lead time reduction by only spending 15 seconds a day and 12 hours once a year? My name is Evelyn Ploud, and together with our Hebrew University team, we managed to achieve just that. If we look at the graph, for all the different scenarios we were asked to calculate, we achieved significant savings over GM's data. In the short time we have together today, we will discuss the problem, our process, results, and next steps to be taken. The problem. We were asked to optimize the 1.7 million vehicles GM manufactures in any of the 4 plants and distribute them to the 8,000 plus dealers. Currently, GM has 44 vehicle distribution centers we use this to agglomerate the cars and further get them to the dealers. As part of the problem, we were allowed to either close or move any of these vehicle distribution centers. In addition, we had 3 different transportation modes to choose from: rails, trucks, or use the autonomous feature, having the vehicles drive themselves for up to 300 miles. In addition, we have 4 different scenarios to take into account: static, in which each plant dealer pair goes through the same VDC for the whole calendar year; and dynamic, in which all decisions are made in a daily basis based on demand. As well, we had to take into account how autonomous vehicles affect these scenarios. Our process was to divide the problem into 3. First, a P-hub location allocation problem, in which we located the close to optimal place to put the VDCs. Second, a vehicle routing problem, in which we decided the close to optimal place, the routes to put from final VDCs to dealers. And third, we dealt with finding the near optimal place for the flexible VDCs. Now I will let Gal guide us through this process.
Thank you, Evelyn, and thank you all for having us. So after dividing the problem into 3 sub-problems, we tackled the first problem, which is the P-hub location allocation problem. So we have this map of plants, VDCs, and dealers, and our goal here is to optimize GM's VDCs network in order to reduce transportation costs and lead time. So how we did that? First of all, we clustered the dealers using k-means clustering. So we chose to cluster them into 100 different clusters. Then we opened new VDCs at the demand-weighted center of each and every cluster. So we ended up with having 100 new VDCs and another 44 original VDCs, which makes it 144 in total. Then we obtained an initial solution of plant VDC dealer assignment by picking for each plant dealer pair the VDC that minimizes the transportation costs between them. And after that, we used our simulated annealing algorithm. So simulated annealing, or in short SA, is a meta-heuristic to approximate global optimization in a large search space. So it was actually already successfully applied in this P-hub location allocation problem. But our goal here, or the objective here, is to, again, optimize the VDCs network, and we do it by merging or moving VDCs to better locations. So after running simulated annealing for over 1,000 of iterations, we end up with a better set of VDCs at better locations and a better allocations. The algorithm led us to close 8 existing VDCs, opened 8 new VDCs at better locations, and it also helped us to achieve 80% of the dealers within a 300-mile radius from their VDC, which will help us later in the AV scenarios. Now we have a better set of VDCs. We continue to the second sub-problem, which is the vehicle routing problem. So in this problem, we have a VDC that stores vehicles, and those vehicles need to be delivered to their respective dealers. So we need to find the optimal way to deliver the vehicles to the dealers. To do that, we first of all used Google OR tools to compute possible routes for the vehicles. But as expected from Hebrew U students, we didn't just use a black box. We also came up with this cool grading system that was inspired from a risk equation. So this inequality takes into account the route price and the minimal route price, which is the route price in case each and every dealer of the route receives a fully loaded truck. And the average day at the VDC, the vehicles to be delivered via this route stayed in. We also have parameters in this inequality, the lambda and the c, so we needed to find the optimal values for these parameters. To do that, we ran sensitivity analysis on both values, on both parameters, and we noticed that there is a trade-off between cost per vehicle and lead time, and there's also inverse correlation between the parameters. We chose the values that minimizes that cost per vehicle because it also consists of penalty, which is linked to the lead time. So after having those values, we simply send all the efficient routes, the routes that satisfies this inequality. So by now, our algorithms cover the static scenario, and now we are heading to the third sub-problem, which is finding the optimal flexible VDC location. This problem is linked to the AV scenarios. So just as in the second problem, we have vehicles that sort of the VDC, and we need to deliver the vehicles to the dealers. And now we can do it using the AV feature. So AV, or autonomous vehicles, they have a limit. They can only drive themselves up to 300 miles, because after that, the value of the vehicles drops. So to do that, we first of all send all the vehicles to the dealers that are within 300-mile radius from the VDC. But what about the rest? What about the dealers that are not within this radius? We can open for them a flexible VDC. This means we can calculate truck routes, just as in the second subproblem, make the truck drive to a certain point, then offload all the vehicles at that point, and make them drive themselves using the AV feature to their respective dealers. So the challenge here is to find the optimal point, the optimal location to open the flexible VDC. I'll mention the fact that there is no need to search for such location in case the dealers of this route are not within 600-mile radius of each other because, again, of the AV limitation. So let's focus on the cases where the dealers are within this radius. So again, we need to find the optimal flexible VDC location. So we designed this problem as a force-directed graph problem. And we initially located the flexible VDC at the centroid, or the demand-weighted center, of this cluster of dealers. I want you to imagine springs. So we have a spring that goes from the flexible VDC to the original VDC, and then another springs going from the flexible VDC to each and every dealer. Those springs are forces represented by vectors that are proportional to the transportation costs. So we then keep moving the VDC in the direction of the net force until all forces disappears, which means we reach the equilibrium point. And this is where we want to open our flexible VDC. So now that we have this flexible VDC location, we can either choose one of the three options, use the flexible VDC, or offload the vehicles at a dealer's place. We assume that by doing that, we can avoid unnecessary offloading costs, or simply use truck routes as calculated in the second subproblem. So now we covered both static scenarios with AV and without AV, and now we are left with the dynamic scenarios. The dynamic scenario tells us that we can skip the last leg, which means we can simply ship vehicles from the plant straight to the dealers. To solve these problems, we decided to cluster the dealers according to a certain amount of clusters and ship all vehicles to clusters that are within this a certain radius. So to find the radius for both scenarios and the number of clusters for both scenarios, we ran sensitivity analysis, and these are the values we achieved. This helped us aggregate the vehicles more efficiently in the plants, send more fully loaded trucks, and reduce transportation costs. As for the capacities of the VDCs, we ran sensitivity analysis on 2011-2012 data for each and every VDC, and we picked the capacity that the optimal number of space for each and every VDC. So we did that for both scenarios, with AV and without AV. And in the AV scenario, we were also able to pack the vehicles like sardines because nobody needs to drive them, right? This helped us reduce the cost per parking by over 30%, both in the plant and both in the VDC. And now for the results, I'll leave the stage to Evelyn.
Thank you. So let's discuss some results. First, in this graph, you can clearly see the amazing savings we achieved. For both the training data and validation data periods, we achieved over $500 million in savings, which corresponds to 33 and 36% respectively. In this graph, we can see in the middle that final BDC to dealer gave us the biggest cost savings in the cost function by over 60%. Talking about lead times, once again, we achieved significant savings of 37 and 36% correspondingly for validation data and training data, which corresponds to close to 5 days for both periods. Now we get to the result period, 2015, 2016. Here we can see that autonomous vehicles are the future. They not only they have all the advantages that has been discussed before, but once again, they give us cheaper shipping costs by approximately $110 million for all different scenarios. We can see it in the light green and the yellow. In regards to lead time, once again, they give us significant savings of close to 2 days. Next steps to be taken are recommendations. So in summary, to move 8 VDCs to new improved locations, use the AV feature to save in lead times and in costs, and finally, run many different heuristics to calculate possible different routes and save an additional $180 million. So if you would like to save over $500 million and close to 40% in lead times by only spending 15 seconds a day and just 2 hours once a year, choose our solution. Thank you for listening.